Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to continue to talk about combined axial compression and bending. If you haven't watched the first part of this video, I suggest you go back and watch that one first, which gives all the background and describes what the equations are. In this video we're going to continue where we left off, which was talking about this compression and bending equation and talking about what each of these terms means and why they exist in the way that they do. In the previous video, we got as far as talking about, in this compression and bending interaction, why we have this squared term here. And in this video, we're going to start off by talking about what this term here does when it modifies the MF over MR. And this is actually an amplification term, so it's going to always be greater than 1. So it's going to make the effect of our moment greater. Okay, so let's continue that way. So here in the previous video, we talked about tension and bending interaction and the first term effect, which was the PF over PR squared. So now we're going to continue and talk about the second term in the interaction equation. This is what that second term looks like, if we recall. And this is the amplification term. And this term is always going to be greater than 1 because PF over PE is always going to be less than 1, which means that the bottom of that, the denominator is going to be less than 1, which means 1 divided by less than 1 is always going to be greater than 1. And what this term does is it amplifies the effect of moment. And why is it that we want to amplify the MF over MR? It's because we want to account for second order effects, also called P delta effects. And I'm going to look at both of the cases of P delta effects, how we get an amplification of the moment when we have bending that causes deflection, which also has to have then axial load. So whenever we have bending in our member, we are going to have some deflection between the ends. And the worst case of that looks something like this. So I have my member, I have an applied moment. Let's forget about the axial loads for now. Just I have a moment. If I apply a moment like that, then I'm going to get a bending. And that bending is going to have some shape, something like this. And compared to the straight line that it used to be, when I apply these moments and I bend my member, I am going to get some deflection at the center, delta. And this is the P small delta effect, where I have basically deflection in between the member ends. And if I look at the moment caused just by that M, then my moment is going to look like this because I have a constant moment. Okay, so this is my constant moment, M. Okay, so now let's say that I have my member in my deflected situation, so I have the bending. So I'm already doing this just by twisting the ends. And now let's say, in addition to that, I add an axial force. Okay, so now let's just look at a curved member. We're going to forget about the moment for now. Let's just assume that the member is curved. For whatever reason, it's curved. And now I apply a load to it. So the load didn't cause the curve. The member just happens to start out curved. And I have that existing delta. So this existing before I apply the P. So then what kind of moment am I going to get on this? Just due to the curved state of the member, I'm going to get a moment that looks something like this. And the moment is going to be greatest at the center here, and the value of that moment is going to be P times delta. You can think of it in terms of, if I was looking at the left side there, I have this P, and that P is multiplied by an eccentricity here, delta, and that's what's causing that moment at the center of the beam. Okay, so now if I take both of those effects and I add them together, it means basically that if I have a curved member caused by moment, I'm going to have the moment I'm going to have the moment that I'm applying, but I'm going to also have an additional moment, which is caused by the axial load being applied to a curved member, and that's my P delta. So what does my total moment look like then? I'm going to basically have my moment that I had applied at the ends, right? That's my M. Oops, M, right? That's my M. And then superimposed on that M, so that's where my M was, superimposed on that M, I'm going to have this moment, which is caused by an axial load being applied to the bent member. So I'm going to have M plus P small delta here. So this is the P small delta effect. In the steel code, it differentiates between P small delta effects and P big delta effects, which we're going to talk about in a second. And the wood code does not differentiate between these two things. So we're basically accounting for all P delta effects in one kind of approach. Okay, and so we're applying for this P small delta and also, it turns out, P big delta by modifying my moment by this amplification term in the equation. And the reason that it's okay is because this is a very conservative approach. So we get a bigger magnification than maybe we need, but it covers basically, it's meant to cover kind of all types of typical kind of geometries that we're going to end up with situations like this. You'll notice that it has no indication here of what the actual displacement is that we're accounting for. Okay, so there is another equation that we can use that's a bit more accurate, which I'm going to show in a minute. But that equation is more kind of aligned to this second kind of P delta effect, which is the P big delta effect, which we're going to talk about now. Okay, so let's say that we have a cantilever. Okay, and I am applying a lateral load to this cantilever. That lateral load is V, and let's say that cantilever is a certain height. We'll call that H. Then what is going to happen to my cantilever after I apply that load? It's going to deflect, something like this. So it's going to deflect away from what it used to be when it was straight. And so I still have my V here. If I'm drawing a free body diagram, I have a V here. And this displacement, I'd call that big delta, Greek big delta. Okay, obviously this free body diagram is not yet in equilibrium because I have a couple. So I have my regular moment, and this is just right now the moment caused by the couple. So it's VH. Okay, so if I were to draw my moment diagram for this, it would look something like this. So I basically just have a triangle, because at the top I have no moment because it's a free end, and at the bottom I have moment equal to V times H. Okay, so now let's say, so this is just like in the beginning where I started with a moment in the previous case. Okay, so I started with a moment here caused by the lateral load V, and now let's say I start with that same condition, I start with that deflected shape, and I add an axial load. Okay, so now I'm saying forget about the load that caused this deflection for now. I'm just going to look at there being a deflection. Oh, I better move this down. Okay, so there's my delta, and I'm going to say, let's say it just starts deflected. I don't care right now how it got to that deflection. Maybe the member's just curved to start with, and I'm applying a load P. Now what's going to happen is that my P is being applied at some eccentricity delta. So if I draw my free body diagram here, again, I have a couple. These two P's form a couple, and they're separated by this eccentricity delta. And so in order to finish this free body diagram, I'm going to have to add a moment to resist that couple. It's going to be at the base here because that's the only place where we can have a moment, and it's going to be P times the eccentricity delta. And so if I now draw the moment diagram for that situation, it's going to look very much the same as before, but it's going to have a different value of moment, which is now the P times the delta. And this moment here is my amplification. So this is basically how much is my moment amplified because of the deflection. So the total deflection, the total moment, sorry, now at the bottom is going to be VH plus this effect P delta if I have an axial load on that structure which is being deflected sideways. Okay, so that is what that term, this term over here, is accounting for. It's amplifying that moment in a simplified way by looking at how close I am basically to Euler buckling. So the closer I get to Euler buckling, the larger that amplification factor is going to be. Okay, so that seems a bit weird because it's not directly related to any of the geometry of the problem. It's just looking at basically how close to like a critical load value I am. But as I said, this is a simplified approach to account for these P delta effects. Okay, so now overall, if I look at the interaction diagram, just like we did for tension, what are we gonna see? Okay, so here is my axes, just like we had before when we were looking at tension. And remember, the tension one was a straight line. So obviously, if my MF over MR is 0, okay, so if I have no moment, then my PF over PR should be less than 1, which basically just means that my resistance has to be greater than or equal to my applied axial load and compression, right? Likewise, if I don't have any axial load and compression, then my requirement is basically just that MF over MR has to be less than 1, right? That's the same thing as saying that MF has to be less than or equal to MR. So we know that we have to hit up these 2 points, right? And the linear interaction, which was the tension interaction, as you recall, was just a straight line that joined those 2 points. And that's not what we have here. What we have here is something that looks more like this. And if you actually plot out these equations, this is what you're going to get. It looks something like that. So it's a bit bowed out, and that bowing out is a function of the PF over PR squared and this second moment amplification term. So basically the bowing out is because of PF over PR squared, and the amplification term is going to change that effect. So let's say that if I have a really low PF over PE, then I might have a curve that looks something like this. And then as my PF over PE increases, my moment amplification increases, and I get closer and closer to this linear interaction curve that we saw before. So basically, as PF over PE approaches 1.0, I get closer and closer to that straight up diagonal line. And it's not totally like the way that I've drawn it here, it looks like it's a bit even, but actually it comes off kind of more diagonally here, starts off a bit more straight, and then tends to kind of curve towards the end. That's more kind of what it looks like. Something like that. Okay, so this was the linear interaction. So just like before, any design that is to the bottom left of whatever my curve is a appropriate design. So I could have an appropriate design here, I could have one here, I could have it right on the line. If blue happens to be my interaction equation, any space in here is basically fine. Okay, so it's the area within that space are all of the appropriate possible designs that I could have. Okay, so that means that, if I end up with, this dot here, okay, what's happening? That means that my PF over PR plus MF over MR can actually be greater than 1. Okay, but of course my actual interaction, which is PF over PR squared plus MF over MR times that amplification term, can't be greater than 1. Okay. All right, so that's what my interaction diagram looks like. So basically it's pushed out a little bit because of that effect of so it's pushed out from the linear interaction because of the effect of the PF over PR squared, which, as you recall, is due to the imbalance between the tension strength and the compression strength. So the compression strength is a little bit greater. So if I add some compression, I actually increase my moment strength a little bit. And the second term, which amplifies the moment, actually pulls it back, tends to pull it back to the linear interaction. So we basically have two kind of competing effects happening here. Okay, the last thing that I want to cover here is that there is actually a more accurate approach to take into account the P delta effect. And that approach is provided in the appendix. And I just want to talk about it a little bit here. Okay, so if you go to the appendix to the standard, there are quite a bit kind of useful things that are they're not manual things to apply under the standard, but they are useful and kind of recommended things that you could do. Usually some of them require maybe some more work. And this is one of those things because I have an alternate interaction equation for compression and bending that looks like this. So the first term, PF over PR squared, remains the same, but the second term is a little bit different. So now you basically have MF plus PF times delta. So there's my P delta. So now I have explicitly the applied moment plus the P delta effect. And now this delta is something that I have to basically grab explicitly, like I have to be able to calculate that delta. And then I multiply that by the same amplification, PF over PE. And then I divide that whole thing by my MR. So basically I have like a moment, and then I'm adding an extra amplified moment caused by the P delta. Of course, the P also makes the moment a little bit greater, which increases the delta, which is why we still have to amplify it. And then we divide that by the total MR to get a more accurate idea of how much of the moment capacity we are taking up. So basically the numerator in this term now has a more physical interpretation, which is that it's actually the total amplified factored moment. And then we divide that total amplified factored moment by the resistance. So it's an equation that makes a little bit more sense, but it's not simplified because I actually have to be able to calculate that delta, which is not trivial. So that's why the standard uses kind of the more simplified way. But this one will give you a better estimate, which means it's not so over conservative as the one that's in the body of the standard. So you can squeeze a little bit more juice out of your beam column design by using this more detailed equation. Delta L is the actual lateral deflection. So you can see that that implies that this is a P large delta effect that this is explicitly taking into account. Okay, the other thing that I wanted to talk about is biaxial bending. This is something else that is not explicitly in the standard, but there is some guidance in the commentary. Okay, so if you go to the commentary in the standard, which you find in the book, so if you haven't looked at the commentary yet, it has a lot more detailed information. So there's the wood design manual. The gray pages are the standard itself, and then right before the gray pages are white pages that are commentary on many of the clauses that are in the standard. So if you go to the commentary for the interaction equation clause, it'll tell you all about these P delta effects and what's happening with the strength of the member and all that stuff that we just talked about. And it will also say that if you have biaxial bending, which means that I have bending in this direction and in this direction, the strong axis direction, plus axial load, then it provides an equation that you can use to calculate those effects. And it looks like this. So we have our PF over PR, okay, without the squared this time. And then we have our factored moment in one direction divided by our factored resistance in that direction multiplied by the moment amplification, the same one as before. So now we have PF divided by PEX, which is the Euler buckling, but in the same direction as this moment for this term, so the X direction. Okay, which means that the I will be that moment of inertia for bending in that direction. Okay, and same for the LE, the effective length. Okay, so you're going to use an effective length and an I for the X direction bending, which is the bending for MFX over MRX. And then you're going to do the exact same thing for the Y direction, which however you determine what the Y direction is, whether that's, you know, the strong axis or the weak axis, because it doesn't really matter because this equation is the same for both. Okay, 1 minus, we have the same thing, PF divided by PEY this time. And then all of this direction together has to be less than or equal to 1. So it's basically the same exact equation. Now adding an extra term for the Y bending. So if I have, you know, if I use up, let's say I use up 10% of my axial compression strength and 40% of my X direction moment, then I only have, what did I say, 40? Then I would only have 50% of my Y direction moment that I could use up, you know, effectively. Of course, I have these amplification terms as well. But that's kind of the idea. So that's basically saying that bending in one direction and bending in the other direction are additive, which makes sense because if I bend in this direction, I get extreme tension in the fibers on this side. And if I bend in the other direction, I'm going to get extreme tension on this side, for example, and that point basically represents one corner of the cross section. And once that corner of the cross section reaches the tension strength, then my beam is going to fail. Right, so this one is bending in one direction. This one is bending in the other direction, and the other difference is that there is no square on the PF over PR term. And that is basically increasing the amount of conservatism to this equation. So since we have bending in both directions now, it's no longer kind of clear how that difference between compression and tension is going to affect the section. Because I could be, you know, applying tension from bending in one direction, and then in the same place I'm applying compression from the other. So it's really just the net tension that we're checking against here. So when do I reach basically that total tension strength, including consideration of amplification for P delta effects. So that's it for design for axial compression and bending and axial tension and bending. We looked at in the first video, how do we do the combination for applied axial tension and bending simultaneously and what that interaction looks like and why those stresses are additive. Then we looked at how we do combined axial compression and bending, and what does the square term mean for the first term of the interaction equation, which was the effect of different strength in compression and tension. Then we looked at the second term effect, which amplifies the MF over MR to account for P delta effects, and we looked at what those P delta effects are. And we looked at the interaction for axial compression and bending, and then we basically looked at some other alternate approaches that better take into account P delta effects and also what to do if I have biaxial bending.